In early 1920, from his deathbed in India, a brilliant mathematician drafted a final letter to his former mentor, G. H. Hardy. The author was Srinivasa Ramanujan, and in this letter he outlined a strange new class of mathematical objects he called Mach theta functions. Ramanujan claimed these functions mimicked the deep symmetries of traditional modular forms, but completely broke their strict rules. This formula defines the third-order Mach theta function f of q. Inside the geometric unit disk, the function evaluates cleanly, providing predictable results for every value of q we plug in. While it behaves predictably within this confined space, the function undergoes a radical shift as we approach the outer edge of the disk. Rushing toward the outer edge, we reach a perimeter where the absolute value of q is exactly 1. This perimeter is a natural boundary. Upon reaching this line, the function encounters a chaotic ring of singularities that blocks any further evaluation. Classical analysis suggests the function diverges into infinite noise at this boundary. Nothing crosses the line because the math simply breaks down. However, specific rational points along this circle, known as primitive roots of unity, offer a different result. They remain well-defined, even as the rest of the boundary collapses into chaos. If we can mathematically pierce the boundary at these precise points, we can extract exact algebraic data from a region that usually refuses to yield anything but noise. To enter the boundary, we take a radial limit. We draw a straight line from the center of the disk, aiming directly at a primitive root, like k equals 3 or k equals 7. The formula for f of q consists of a numerator and a denominator. It is the denominator that holds the key to the boundary. This is the Q-Pochhammer symbol, an infinite product. As we approach the edge, we need to know if this product shrinks to 0 or explodes into infinity. We can visualize this product geometrically. Each term in the Pochhammer symbol becomes a vector, adding itself to a sequence on the complex plane. As the index m increases, the vectors multiply and rotate, orbiting the origin in a predictable pattern. Because we are aimed at a primitive root, the tips of these vectors perfectly trace the vertices of a regular polygon. Usually, an infinite product would spin endlessly or vanish, but here, the geometric symmetry of the polygon suggests the sequence might be repeating. This mechanical repetition becomes undeniable, locking into place the exact moment the index m reaches the designated root order k. At this precise moment, the current vector rests on 1 plus zeta k to the power of k. Since any primitive root raised to its own order equals 1, the vector simply becomes 1 plus 1. The complex terms dissolve, leaving a solid integer, 2. This is Pochhammer periodicity. Every full orbit of this product yields exactly the integer 2. In Ramanujan's f of q formula, this term is squared, meaning each full orbit contributes a factor of exactly 4 to the product. The numerator undergoes a similar process. Its exponents are locked into a repeating loop determined by n squared modulo k. Both the top and the bottom of the formula are now perfectly synchronized. The infinite series has collapsed. Instead of a chaotic diverging sum, we have a perfectly repeating geometric loop. We can now rewrite the entire Mach theta function to separate these repeating cycles from the core algebraic values. The formula splits into two parts: an infinite geometric series summing powers of 1/4, and a bounded finite sum we call tk. The infinite geometric series evaluates exactly to the fraction 4/3. This leaves the period sum tk. Because the periodicity handles the infinity, this sum is now finite, running only from index 0 to k-1. tk is an exact algebraic integer. It represents the residue of the function at the boundary root. These integers live in a cyclotomic field, a specific branch of number theory where the values are exact, not approximations. By exploiting this periodicity, we have crossed the natural boundary to extract calculable, algebraic data from a region once thought to be impenetrable. Having extracted these exact boundary values, we can look for the arithmetic rules that govern them. To measure these algebraic integers, we use field norms. These provide a way to calculate their size and determine their prime factorization. These are the absolute field norms for the first few odd prime roots of unity. A pattern emerges at powers of 3, 9, 27, and 81. Their three-adic valuations grow by a precise formula. phi of 3 to the n minus 1. This matches the Iwasawa mu invariant, a fundamental number theory concept. Ramanujan called this a third-order Mach theta function. This data indicates that designation describes a deep three-adic structural signature embedded in the function's boundary. The most significant application of this data concerns the Birch and Swinnerton-Dyer conjecture, which links the points on elliptic curves to prime numbers. To solve this for a specific curve, we return to the data extracted from the seventh root of unity. The algebraic properties of T7 define the coefficients of this third-degree equation, the deviation polynomial, P7 of v. This polynomial has a single real root sitting between 1 and 2, which we call delta 1. We can trap all possible roots of this polynomial using the Cauchy root bound, a rule that sets a physical limit on where any root can exist. For P7, the Cauchy bound places every possible root inside a box ending at 2.4955. The BSD conjecture states that if the Shaw group has a size of m squared, then m squared times delta 1 must also be a root. But testing an m value of 2 or greater sends the point far outside the Cauchy bounding box. Since any group size larger than 1 violates the Cauchy bound, the size of the Shaw group must be 1. By resolving the natural boundaries chaos into exact algebraic integers, these Mach theta functions provide the missing constraints to solve specific elliptic curves. 100 years after Ramanujan's final letter, his deathbed discovery is providing concrete proof for the deepest conjectures in geometry. In the early 20th century, the mathematician Srinivasa Ramanujan defined his third-order Mach theta function, known as f of q. Alongside it sits its parity-shifted companion, f of q. Both functions share a strict geometric constraint. They operate entirely within the confines of the unit circle, where the absolute value of q equals exactly 1. In classical complex analysis, mathematicians use analytic continuation to extend a function's domain. That for these Mach theta functions, the unit circle acts as a natural boundary. The standard mathematical tools break down. If you try to map classical Taylor series approximations expanding from the origin, they collide violently with this unit circle. The edge of the circle is infinitely dense with singular poles. There is no gap to slip through. Because no analytic continuation can cross this line in the variable q, the function traps us inside. To escape, we have to discard classical methods and find an entirely different geometric approach. To test the strength of this boundary, look at its most regular coordinate, q equals -1. Evaluate Ramanujan's companion function here, and it does not blow up to infinity. It settles perfectly at the finite rational value of 64/75. The internal mechanics allow this because at -1, every single Pochhammer factor remains non-zero. They simply resolve to 2 to the power of r. This graph plots the local Taylor coefficients expanding around -1. As the index grows, the curve rockets upward in factorial growth. Calculating their limit supremum yields strict infinity. Consequently, the local radius of convergence shrinks exactly to 0. Even when a specific point on the boundary appears mathematically stable and yields a finite sum, its microscopic geometry is riddled with singularities. It is a genuine natural boundary. You cannot breach it from the inside. To cross the boundary, we have to stop analyzing the variable q. Instead, we analyze the function's radial limit structure as it approaches the wall from the inside. We telescope complete Pochhammer cycles along a straight radius, aiming specifically at odd-order roots of unity on the perimeter. This process strips away the noise and leaves a universal constant prefactor, 4/3. Extracting this underlying data yields a single generating kernel, h of t equals the inverse of 4e to the t minus 1. This kernel generates a precise sequence of rational fractions, known as the moments, m sub k. This moment sequence is the structural DNA of the boundary. By operating on this kernel, we bypass the wall through 3 completely separate mathematical dimensions. The first continuation transforms the kernel via the Mellin transform. By integrating the kernel h of t along the real axis for t greater than 0, we shift the mathematics out of the spatial domain and into the spectral domain. This integration yields an exact grip on the gamma function. This 3D topographical map charts the resulting meromorphic function, gamma of S times the Lurch transcendent of 1/4 across the complex S-plane. The surface is smooth, except for simple poles that strike upward exactly at the non-positive integers, 0, -1, -2. This spectral continuation bypasses the unit circle boundary because the exact residues extracted from these poles perfectly reconstruct our original moment sequence. The second continuation applies resurgence theory to physically alter the geometry of the map itself. By executing a change of variables, defining q as e to the -t, the circular boundary unrolls into an infinite, perfectly straight vertical line. The interior disk, where the absolute value of q is less than 1, is now the entire right half plane, where the real part of t is greater than 0. Applying the Borel transform to this new space exposes hidden singularities at -log4 plus integer multiples of 2 pi I. From these, Stokes rays branch upward. The natural boundary is actually an infinitely dense accumulation of these rays against the imaginary axis. The Borel sum employs a Lurch transcendent to analytically cross the boundary, slipping through the infinitesimal gaps between the infinitely packed Stokes rays. The third continuation abandons continuous geometric planes entirely, entering the discrete reality of modular arithmetic. It relies on an elementary Frobenius identity, operating strictly within finite fields modulo a prime p. By utilizing finite moment level 1 Kummer congruences, it imposes structure onto the integers. We apply a mathematical filter called Frobenius stabilization, mathematically subtracting the Euler factor at p. This discrete filtration cleanly maps our continuous moment sequence into the Coleman p-adic polylogarithm. Evaluating this discrete structure at roots of unity returns the exact p-adic L values of Dirichlet characters. The boundary isn't strictly a geometric barrier. By bypassing it arithmetically, we uncover the hidden prime number structure governing the Mach theta function. We have bypassed the impassable wall 3 ways, using continuous spectral integrals, resurgent Stokes geometry, and discrete modular fields. These are 3 distinct mathematical universes, yet all 3 output the exact same moment sequence, m sub k. They also anchor themselves to the exact same radial center constant, 4/3. There is one final unifying trait. The number 3 is the unique bad prime across all 3 systems. It is the only pole in the Mellin transform denominator, and the sole non-integral prime in the p-adic domain. When 3 independent branches of mathematics share the exact same sequence output, the exact same center constant, and the exact prime obstruction, they are describing the exact same geometric truth. This proof relies on synthesizing human intuition across widely separated mathematical disciplines. To eliminate the possibility of human error, the results are run through a formalization program using the Lean-4 proof assistant. The foundational proofs, the Frobenius identity and the moment recurrences, are translated into code and processed by the machine. The system returns a no sorry output. This means the computer has checked every single logical step down to the foundational axioms of mathematics without assuming a single gap. Translating these findings into Lean-4 secures our path past the factorially divergent boundary, anchoring the theoretical geometry in absolute, verifiable computational reality.